David Grant,
Yes.
can you record to the cloud, please? Just go down to the bottom and hit record. It should allow you to do that at the same time that I'm recording it. Thanks.
I'm recording to the cloud,
Okay,
Natalie.
great.
So it's
Thank
all
you,
good.
Brandon. All right, thanks.
No problem.
All right. Hello, everyone. We now have all of our panelists. Chris, are you good to go there in St. Louis?
Yes.
All right. We will get started.
So the one thing is for us on our side is if anybody has a question or wants to speak up, please come to the microphone up here, or else nobody will be able to hear you or on the Zoom. This is not being streamed; it's only being recorded. And that's all I have.
All right. Thanks, Chris. All right. Hello, my name is David Grant, and I'll be moderating this BoF. Supporting me, we have Natalie Bates as the virtual host and Chris DePrater as the physical host there in the conference center in St. Louis. Please be advised that this session is being recorded. The recording of this session will be available in a couple of days and will be available through January 31st, 2022 on the SC21 Hub website. We have both in-person audience members in St. Louis and virtual attendees from all over the world. Thank you all for joining us today, and welcome to the Energy Efficient High Performance Computing Working Groups panel titled Liquid Cooling Challenges and Facility Experiences. What's next? Joining us virtually, we have a long list of panelists who have an extensive experience in the HPC world. We have Norm Bourassa from Lawrence Berkeley.
Bourassa.
From Lawrence Berkeley National Lab. He is the Energy and Water Performance Lead in the Building Infrastructure Group for NERSC. John Gross of JM Gross Engineering. He's owner, mechanical engineering director, and has been working with liquid-cooled HPC, the HPC market for over a decade, and is nearly actively involved in OCPs on liquid cooling facility standards. Herbert Huber from LRZ. He is the head of Performance Systems Department at LRZ, the worldwide first direct warm water cooled supercomputer, SuperMUC, was installed at LRZ in 2012. Michael Lesniak with Nalco, Water Data Center Solutions, an EcoLab company, VP Global Corporate Accounts, working with hyperscale cloud owners and high performance computing leaders to provide treatment and cleaning packages, treated water, PG25, and water analysis, and metallographic analysis services. We have David Martinez from Sandia National Lab. He is the engineer program project lead for computing services at Sandia. We have David Masuda from Chemtreat, the Northern California account manager with 16 years of direct application experience in data center water treatment. We have Mike Ramirez from Sandia as well. He is with the Building Automation Group doing building and energy management. We have Dale Sartor from Lawrence Berkeley National Lab. He is an extraordinary mechanical engineer and all-around good guy. He is one of the founders of the EEHPC working group and has been active in liquid cooling close for 2 decades. I don't think he thought I was going to read that straight out, but I did. Vali Sorell from Microsoft. He's the principal hardware engineer at Data Center Integration Services. Sammy Zimmerman with NVIDIA. He is a project manager for the HTX products used in HPC and AI. He has a background in liquid cooling as both a thermal engineer and a project manager, bringing both liquid and air-cooled products to the market for the HPC and AI industries. So the organizing committee for this BoF has put together a list of questions for these panelists to discuss. We do encourage the audience to post questions either in the Zoom chat or in the Hub Slido Q&A, which is on the Hub website. If you click on the BoF title, it'll take you to the BoF page, and it should have that on the right-hand side of the screen. Or we all have microphones, and you can introduce yourself when we have the time where questions are solicited during each question. If we aren't able to get to all the questions during each time slot for each question, then we'll try to get them at the end. So without further ado, let's get into the discussion. This panelist and the organizing committee hope that the audience gets these things out of the session. We all hope we provide general state of the practice, expose the audience to some of the experiences that the panelists have had through their diverse working careers, and what's needed for liquid cooling to come and what's around the corner. We've just gone through the panelists, and question 1. Although there are facility models for electrical systems that are widely deployed, the same is not available for data center cooling mechanical systems. What is the research and development being done in this area? Could it be valuable to and relevant to the HPC design process, especially relative to liquid cooling? And I'd ask the panelists to make sure you're not on mute. And John Gross, would you be able to take the lead on this one?
Yeah, sure, David. Sorry about that.
Yeah, honestly, there's not a lot being done right now in terms of developing extensive energy modeling protocols and software for liquid cooling applications. And a lot of that has to do with the fact that, quite frankly, a lot of the load profiles on these and the cooling loads end up being fairly simple and straightforward process loads. The power consumption that we're getting from the electrical models can be turned directly into heat in most cases. And you don't have the typical thermal inertia scenarios and thermal mass situations that you have in comfort cooling applications, which is what most HVAC energy modeling and load modeling software is designed to address. So I know Vali, with a lot of the work that you've been doing within ASHRAE on the energy modeling side, I know you've been looking at this some. What are your thoughts?
Yeah, I agree with you. The ability to do load calculations and hourly energy simulations is pretty well documented for the comfort cooling environment. For data center, the good news is that the loads are so easy to model that you don't need that same level of simulation that you would get from a program like Trace or DOE 2.2 or eQuest or Energy Plus. This is the kind of calculation that can easily be done on or in a spreadsheet, and you can still do an hourly simulation. You would just have 8,760 rows in that particular spreadsheet, but it still is a very straightforward calculation. What you do need to know is the amount of heat that's removed by liquid cooling, and then from that point on, it becomes a very simple heat transfer problem, because the heat that's taken out of the IT equipment that's passed through a heat exchanger or cooling distribution unit, or eventually to the outdoor dry cooler or cooling tower, that calculation is pretty much documented. And here again, there's not much work that has been going on to address just the liquid cooling component. But within ASHRAE, specifically SSPC 90.4, which is the energy standard for data centers, there has been an effort to come up with a simplified energy calculation methodology. So the person who's really been developing that, Henry Amistadi, he has been actually doing a lot of MathCAD modeling to look at the heat transfer component. So he's looked at crack units, he's looked at air handlers, he's looked at coils, he's looked at chillers and cooling towers. So the good news of that whole effort is that once you've got the heat transfer component and the cooling towers or dry coolers modeled, it's a very easy extension that would get it to the point that you can actually do the modeling for liquid cooling. So in this particular case, it doesn't matter all that much whether it be cold plate or immersion, single phase immersion two-phase. The actual calculations, other than the heat transfer equation, are actually fairly simple. So this is something that's been going on for a couple of years now. Eventually, in a future version of the 90.4 standard, the intent is to be able to have a pointer inside of the standard that says, if you want to know a simplified method of doing your energy calculation and showing compliance with the energy standard, here's a worksheet that you can go to. So that worksheet is really what I'm talking about. It's in development. It's a slow process, but slowly but surely, I think that we're making a lot of progress towards that end. So that's good news as far as I'm concerned, because I think it's specifically with liquid cooling, it's finding more of a place within the industry. It is getting more acceptance, and I think we'll start seeing more. And I think the emphasis will shift a little bit from the air cooling to the liquid cooling side, so that we get those models inserted into that MathCAD application to be able to do this. And by the way, I mentioned spreadsheet program, MathCAD, they're not the same, but I think the beauty of either one is that you can actually really audit the actual formulas and make sure that one really fully understands what are the calculations that are going on behind the scenes, so that It can be corrected. If it's not right, it can be adjusted. It can be really used to the benefit of a particular data center to make sure that it does what it's supposed to do.
Yeah, and thanks for all of that, Vali. It's, you know, it's good to hear where Henry's at. I know, you know, we've had conversations in the TC meetings about that with Henry and whatnot.
Right.
And you know, you mentioned the spreadsheets. You know, it sounds somewhat crude, but I know both you and I, through our careers in design, have actually been using, you know, spreadsheets, you know, with 8,760 rows, and we go into the weather data files and extract the dry bulb, wet bulb data out of those, and then characterize the heat rejection media. And when we talk about liquid cooling and the energy of the overall system, the energy consumed by the overall system, what we're primarily focusing on, quite frankly, is where we're making those transitions from mechanical refrigeration to evaporative cooling to dry cooling. Those are really the big check marks that we're looking for and trying to understand how that then plays back into control logic and sequences. And that's about as elaborate as we've been able to get, because, you know, as you kind of mentioned, you alluded to, even within the air-cooled market, which is a very mature market within the data center industry, because we're talking process loads, the tools just really haven't been developed. But Henry's definitely leading the charge on that.
And just to add to that and highlight a little bit, once you model a dry cooler or once you model a cooling tower, it doesn't matter whether the heat comes from an air-cooled system or water-cooled system. So the module of the calculation is developed, is fairly mature, established. It can actually be easily converted and utilized in any kind of liquid cooling modeling system.
Exactly. I wanted to thanks, Vali, for pointing out that the problem set is fundamentally small and not really, you know, throwing a full hourly detailed simulation at it is overkill. That said, there is some research activity going on. Some people may be aware of the Modelica building library that the LBL is trying to put together. The idea being getting more targeted, smaller, agile problem solver type library of algorithms that can be put together for simulations, quicker simulations. As of yet, those models are basically air cooled. There's nothing liquid cooled, but this is a space that's not really moving along quickly because of precisely the reason that you said. These are fundamentally simple heat transfer solutions, and it's pretty easy to strike off your prototypical use case and come up with good solutions. That said, there may be more agile models in the future coming out. More ML and AI based modeling approaches that use the track history of measured data in order to produce more predictive modeling, you know, input that can inform better operations. But right now, there's just not a lot in the liquid cooling front in that area yet.
Yeah, and Norm, you know, you referenced the predictive side of things. Obviously, when we talk about modeling, that's somewhat implied, I think. But one of the things I think that makes HPC a little bit of a unique challenge when we try to look at annual energy modeling and energy consumption predictively is HPC from a workload perspective does not behave and does not operate like other compute type applications do. You know, we talked about a little bit earlier today when we had a chance to huddle up, and that is, you know, HPC has a tendency to be executed in batches. And so depending on what that batch load looks like, how many, you know, how many solutions are you trying to run concurrently? You know, what's your actual utilization rate of your cluster? You know, it's hard to characterize that, I think, for most clients especially I know some clients that have a hard time characterizing it on a week by week basis, let alone an annual basis. And so I think that may also be one of the reasons why there's not really been a huge amount of effort put into to the modeling side of things. Because as we all know, with any kind of predictive modeling, garbage in is garbage out. So if we don't even know what the compute load profile looks like, all the rest of it is kind of wasted effort to a large degree.
I'd like to add that it is actually very common to come up with a load growth profile, assuming you start off a facility, let's say at 30% capacity, and then you have maybe 20 or 30% growth per year until you eventually reach 100%. Those assumptions are great. They're working tools. They're never a reflection of reality. And no matter which way you take it, the idea is a predictive model is great. And I think it's actually a lot more applicable to comfort cooling, where you know that a building will be fully occupied. It'll be run mostly from 8 a.m. to 5 p.m. You can plug in what the temperature or outdoor climate profile looks like. And it makes sense. You can actually give numbers to the developer, owner, end user to say, here's how much we think it'll cost to run this facility. With a data center, it is so completely dependent on those HPC loads, like you said, or any kind of IT equipment loads. They're so variable, they're so all over the place that it's really hard to do a predictive model. The best that you can do is do a comparative model where you are looking at alternate systems. And the ones that I really love to actually do are looking at a liquid cooled versus an air cooled system. So you can actually look under different possible load growth to say under all possible load growths, one system comes out better than the other. So it's really good for financial modeling to make the right financial decision, but to actually say this is how much it's going to cost you to run the facility is probably not realistic, because load is load and it changes. It can change by the hour, it can change by the minute. I've seen loads change by the second. So it's really hard to be predictive on that. But for comparison's sake, it makes complete sense that you can make the right, know that you make the right financial decision, looking at multiple load growths, assess what is the better financial model to work with.
All right, thank you, Vali. So we have had a few questions come in, a couple through the hub and then one through the Zoom chat. I'm going to ask the panelists to look at the question in the Zoom chat and digest it a little bit, and we're going to move on to the next question, because I think that it may better suit the two questions that were posted in the Hub app, Slido, regarding the TCO and PUE. Basically, does liquid cooling have TCO advantage over air cooling? And then what levels of PUE can we attain with liquid cooling? How does it compare to air cooling? So if the panelists could think about that and maybe address that in this next question. Mechanical liquid cooling control systems could improve overall HPC facility operational efficiency, but they are often designed with less than optimal efficiency. How would the cooling, power, and control components have to be designed to better accommodate HPC liquid cooling requirements? And I'm going to hand over the screen share to Herbert.
Yeah, thank you very much. Do you see my screen?
Yes.
Yes, sir.
Okay, oh, good, thank you. So to my experience, mechanical cooling systems are often not designed modularly enough and are therefore overdimensioned. So they can very often not be operated close to the most efficient operation point when the cooling load changes. So yeah, and in addition, hydraulic separators were in the past, or also are still, will be installed in hot water cooling circuits with controlled pumping units, and these separators reduce the cooling efficiency relatively strongly and are also completely superfluid or superfluous in cooling circuits without any chillers. And what you see in my presentation is the LRZ cooling infrastructure. We have a dedicated warm or hot water cooling loop where then the loop is connected to 4 cooling towers, 4 gold cooling towers, and each cooling tower has a cooling power of 2 megawatts. And there, yeah. So we have a cooling power in total of 8 megawatts. And the heat exposure of the current supercomputer, SuperMOOC next generation, under normal operation is 2.5 megawatts. So we have, yeah, currently we operate only 2 cooling towers, but they have still a cooling power of 4 megawatts. So they are not operated in the optimal operation point or design point where they have the most efficient, the highest efficiency. Then we have also 2 cooling towers and other cooling towers from Yegi, and a haze tower from Goal, and a cold water fountain. And the sum of these chilled water cooling towers and cooling systems is, let's say, in the order of 4 megawatts. And total chilled water consumption or the chilled water requirement of LRZ is now in the order of 1 megawatt. So we have also an over-designed cooling system here. And we have 2 cooling towers from, let me check, don't see, from Thermofin, just for the chilled water production for the SuperMOOC next generation system, for the storage system, and for the heat exchanger, or for the rear door heat exchangers of these systems. And they have a cooling power of 1.6 megawatt, and we operate 1, and the cooling requirement, cold water requirement, is 600 kilowatts. So they can be operated in a very, very efficient point of operation. We have removed the hydraulic separators, and what you see here are only the heat exchangers of the different loops. And we operate the high water or the warm water cooling loop with an inlet temperature between 36 degrees Celsius in winter and up to 45 degrees Celsius in summer. And the cold water cooling loops are operated with 40 degrees Celsius water in, yeah, over the whole year. And the special purpose cooling towers or the cold water loop for SuperMOOC next generation, the inlet water temperature is 20 degrees Celsius. So what have we done to enhance the energy efficiency ratio? The energy efficiency ratio is calculated by the cooling power divided by the electrical power needed to produce this cooling power. And before we have removed the hydraulic separators, also in the warm water cooling loop, the energy efficiency ratio was between 15 and maybe up to 20. And by removing this type of systems, we got up to 30 and also to maybe 35. And on the cold water loop, you can also see here that we increased the energy efficiency of the cooling loops. And then we have optimized, in the year 2019, we have optimized the warm water control software, and we have reduced the active cooling towers during the winter period. And you see a further very large increase in the cooling or energy efficiency of the warm water cooling loops. So we are now in the order of 45. Energy efficiency ratio is in the order of 45. And on the cold water side, we have raised the cold water supply temperatures from 12 degrees Celsius to 15 degrees Celsius. And also you can see here, we are now in the order of 15. But we don't stop here. So in future, we will operate all cooling towers without any glycol-based water. And the first experiments with that kind of solution tells us that we get an energy efficiency ratio for this solution in the order of 80. So which cannot be shown here. And that's what I want to mention is it's a yeah, you cannot stop this optimization effort. It's an ongoing effort. Just imagine if a new system comes in, you have to also optimize the cooling infrastructure for the new system. So you cannot stop at one point in time and say, okay, now the system is optimized. No, it's an ongoing optimization effort. And what this graph shows you is the amount of hours a year we can produce chilled water without any chiller operation. And if you go up to 20 degrees Celsius inlet water temperatures, the number of we can you produce this kind of water 1,530 hours a year without any chiller. Now we have an inlet temperature of the cold water of 14 degrees Celsius, and so we have, yeah, we can produce this kind of cooling water for 4,600 hours a year. And the intention is to switch to enhance the inlet temperature from 14 degrees Celsius to 20 degrees Celsius. And most of the infrastructure or the HPC or the IT infrastructure can sustain also a cold water temperature of 20 degrees Celsius.
All right.
So that's it from my side.
Thank you, Herbert. So John, I know you have several system iterations under your belt. Do you have any thoughts on this question?
Absolutely. And I think some of the information that Herbert shared in his slide pack kind of underscores what the experience is that I've had, which is, if you notice from his slide pack, each one of those systems had different operating temperature requirements. And now I don't know very much about the deployment, but my expectation is that it's probably similar to a number of the deployments that I've done where we have multiple generations of equipment in the same facility. And as we know, as we go through these different evolutions and these different generations of equipment, the operational requirements change. So one of the things that we run into is if we're going to tie multiple generations of equipment with different operating requirements into the same system, it becomes very difficult to find out through a design process exactly what the optimization scenario wants to look like. We can try to put something together and simulate what it might look like. But a lot of times you run into scenarios like Herbert and his team have, where it takes time of owning the facility and operating it and understanding what knobs you can turn to adjust things. And so when you go back to the design side of things and optimizing design against a highly heterogeneous set of requirements is a very difficult task. And if with more homogeneity, it becomes a lot easier to optimize it. But that's just not the world that we live in. That being said, as we work through these different solutions and we look at designs, and I as a consultant am working in conversations with ITE manufacturers, one of the things that we are trying to understand and share with the manufacturing community is that decisions that are made in terms of the operating requirements and the cooling requirements from the facility to that ITE solution can have a direct impact on not only the efficiency of the solution, but how easy it is to deploy in existing facilities. So I think that's kind of an ongoing conversation, and I think that will become a stable scenario as soon as the technology becomes stable. So probably never, but it's something that will always keep us busy and something that we always have to pursue.
Right. Thank you. All right, moving on to question 3. There is a definite trend towards higher water temperatures for HPC liquid cooling systems, as described by ASHRAE's water WX water classification scheme. What is this trend sustainable? Are higher water temperatures attainable? what can the user community do to influence the continued trend towards warmer water cooling versus reversing the trend and moving to colder water?
David Grant, can you hear me?
Yes, go ahead, Mike.
Mike Rymarz, Sandia National Labs in Albuquerque, New Mexico, and High Desert. Welcome all. As a large research laboratory, I think we're a lot like a lot of other places. We've kind of started off doing air cooling, predominantly going down that road for many, many years. And in doing that, we've used large centralized district cooling loops to feed our air-cooled data centers with crack units and underfloor cooling, as well as on most of our office buildings and labs surrounding them on that same systems. What we're finding is as we go toward this liquid on chip cooling, it's no longer an air conditioning question. It becomes very difficult to feed them with conventional systems. A lot of these things put out 30-degree deltas. That's great to have a high delta T until it exceeds the capacity or capability of your system. Typical chiller plant can't bring that down. If you're putting back, let's say 105-degree water, if it's a small portion, a small data center of your large district cooling loop, it's great. But we've been leaping and bounding by 2 and 4 megawatt jumps. It quickly overwhelms the system. So you have to move to something else. Thermosiphons, fluid coolers, things like that. The amount of heat that you can get out of these things is unrelenting 24/7 amount of heat. It's incredible. You can't hardly even describe it. 30 degrees delta at 400 or 500 GPM is an incredible amount of cooling. Some of these data centers aren't very big, and it might be in the center of your complex, let's say. So the manufacturers are getting really, really good at finding ways to get the heat off the chips into something else. Getting it out of the building, getting it out into the atmosphere can be very, very difficult because it takes a lot of real estate. These cooling towers, they're not small. Centralized chill water plants aren't working for us. We've had to go for things like elevated cooling towers in alleys and things like that and get really creative. So warmer water is great, but you got to design around it from the start. It's very hard to take a system where you're an R&D lab, you kind of tested out a small thing and your management wants to add more bigger things right away. You have to plan for that, maybe as much as 5 years out. Where do you want to be? You can't think of the next year. You've got to plan. I'm going to have 14 megawatts in 8 years from now. I need to plan for that ahead of time.
Yeah, Mike, that's actually the exact issue that I ran into with a client not long ago. They had it was their enterprise data center with some expansion space, and all of a sudden management showed up one day and said, "Hey, we want to move our HPC on campus," and the facility was never designed for it. And so we start digging into what it's going to take to put this RDHX cluster into the space. And right about the time that we got that wrapped up, they came back and said, "Okay, we want to add another 6 megawatts. And oh, by the way, this is going to be cold plate. So get back at it again." And so I think, there's a lot of challenges to that we're seeing on the end user side as well. And, I think this dynamic going on where there's a drive towards warmer water for cheaper cooling, for more sustainable cooling, for heat reuse, and for all sorts of loads. But then you also have to balance that with the ever increasing TDP that we're seeing on the chips and the need to start lowering TCase again, and whatnot. And so that's that's obviously workload and technology driven. So I think from my perspective as a design engineer, one of our biggest challenges is when a client comes to us and says, this cluster that we're going to put in, or this solution that we're going to put in is an ASHRAE W45 solution. So, we're good to go. We can do dry coolers or we can do cooling towers. We don't need to worry about mechanical refrigeration. But I think as of right now, I don't know that we can honestly say that, within the lifespan of that data center, we're not going to be back down in those cold temperatures. And I think it's really up to the chip manufacturers to figure out how we can make this work.
Yeah, John, I think you mentioned some really important things there, right? And anybody who's looked at tracked car erupts data or just dealt with the ever increasing power levels that we're seeing on the chips, and you know, that's difficult enough. But when you combine that with P cases starting to come down pretty soon, now your thermal challenge, actual thermal challenge from a chip perspective, you know, is increasing exponentially, right? 30% higher power doesn't mean 30% harder to cool. It probably means, you know, twice as hard to cool the thing, right? And so when we look at the large supercomputing data centers, and we have people on this call who really moved the industry, like Herbert and Dave Martinez and the folks at Sandia and many others, right? They've gone on this long journey, you know, that of liquid cooling to higher water temperatures, to getting rid of fans, and you know, in some cases going fully fanless, to have these really efficient data centers. My fear is if we try and continue to push the actual facility water temperatures higher, as we have this other aspect of the power levels going up and the T cases going down, you know, there's this natural clash, and we can get around it. You know, you might have to make some trade-offs on performance or on cost or simplicity, things like that. But I think the third thing to look at, you know, from an overall data center industry, is the fact that right now a lot of the commercial entities are moving over to liquid as well, right? And they're just starting that journey that the supercomputing industry, you know, has been on for a long time. And as we push the complexity and the cost of systems up just to get a warmer water temperature, are we actually making more of a barrier for entry for these enterprise private sector customers that are trying to get into the liquid? And I think that's something that we should pay attention to. You know, from a overall perspective, if I'm if I'm a data center manager, I want my data center to be as efficient as possible to save the most kilowatt hours, right, or megawatt hours. But if I look at the industry, what's really going to save the most megawatt hours worldwide is, you know, really focusing on making high performance systems cooled with liquid, you know, non-chilled liquid, that are easy to deploy, you know, that are simple, that are low cost, to lower that barrier of entry and open the floodgates for all these private sector customers.
Yeah, and Sammy, I think your comment about the private sector folks is very very pertinent at this point in time. And right now, I'm working both in HPC, but I'm also working in hyperscale. You know, we're doing a hyperscale liquid cooled data center design right now, and that whole challenge is you've got these two kind of divergent needs. You know, the enterprise or the low density folks, the folks that don't need a whole lot of overclocking in order to get their work done. You know, they're wanting to see entering fluid temperatures, you know, 50, 55 C, 60 C in some cases, which we can't do with the HPC. We're just, that's way too warm. And so as a design side, you know, we have the facility designed to where it can run anywhere from 27 C all the way up to 60 C entering water. And when you look at what it takes to actually make that work, and then you go back to our previous question about designing for optimized efficiency, that's some of the challenge that I think we're battling right now. And you go to a lot of the other conferences, like I was at one of the other conferences last week, and you talk to the thermal engineers from the chip manufacturers, they're singing a different tune than what a lot of the cooling solution vendors that are trying to prepare solutions for the enterprise market are singing in terms of temperatures. And I think it's an interesting challenge, I think, for sure.
But it's also a question of sustainability. And I know that there are technical solutions available to keep the allowed inlet temperature up to 40 degrees Celsius. But they have to, you have people or customers have to ask for it. Otherwise, there will not be produced.
Exactly. And, we've a lot of the conversations that we have within, the HPC world have to do with, our transition points to get away from mechanical refrigeration. And when you start stepping up in the temperatures a little bit more to some of the other workloads in the other market sectors, they're taking it a step further. What can we do to get rid of evaporative cooling and be completely dry cooled? Because yes, we're consuming a lot of megawatt hours with chillers, but we're also consuming an exorbitant amount of water with evaporative cooling. And that's an issue all around the globe right now.
Yeah, I
we've
think
also-
this
go
is
ahead.
Dave Martinez real quick here. I think it's in the future, you're really going to see how you're going to start operating your data center, and basically your computer and your data center is all going to be one. So moving to the AI and machine learning type thing, I see in the future where you try to run these big jobs at the optimum curves of all your mechanical systems and your electrical systems incoming. So there'll be a lot of operational schemes in the future where both mechanical, electrical, and computer all need to be operating as one. So that's coming toward the future.
Yeah, Dave kind of said it all there. We are running into some limitations. Your conventional large centrifugal chillers don't run at 80 degrees in and 105 out. And when you start doing things like that, you run into water quality, you start fouling them. You have to have a dedicated plant. You can't use your 1,000-ton chillers for anything but this data center. So, and then you've got to find a place to put it. These things are not small. So that all needs to come into consideration.
Yeah, I run into the exact same thing, Mike. The facility that I was referring to earlier, where we had the air cooled, the RDHX and the cold plate all in the same facility, depending on what proportion of the load was coming from which solution, we were seeing waterside delta T's as low as 7 or 8 degrees C and as high as 25 C. And so, to your point, a chiller is not going to do 25 C delta T. It's just not. You're going to have an isolation heat exchanger in there, which you lose some efficiency through that and so on. And I think the other challenge that we run into on the optimization side is I think we have I think we all know there's a shortfall in the industry in terms of operations talent on the facility side. And so the smarter and smarter these systems get to optimize them and make them more energy efficient, the harder it is to find the folks to work on them and support them.
All right, thank you all. We are going to mix things up a little bit. I don't believe I've seen any new questions come in that haven't been addressed. I think some questions are being addressed in the chat. We're going to skip to question 6 real quick because we've had a panelist have something pop up. Dave, you are available for question 6 right now, aren't you?
Yes, I am.
Okay, we're going to do this. So what do you see as innovative technologies that will change the liquid cooling landscape?
Oh yeah, so basically what Mike has described to you kind of painted the picture of how we went from air cooling to liquid cooling, but in all actuality, it's been an evolution. Many years ago at SC, I think it was Austin, I did a talk on the evolution of power and cooling. So basically, my thought was that we are going back to liquid cooling and high density machines. It was pretty funny because the room was full and I started talking about doing liquid cooling and the room was half empty by the time I got done getting liquid cooling out. So that was a telling sign of what people thought of liquid cooling, and it's still that problem with some people. However, what we have now is basically the CDUs going into the rack, and we're extrapolating the heat, whether it's some type of interface with the chipset or maybe plate cooling, or now we're starting to get into immersion cooling. So I think that the technologies will also change with the chip, where the chip and the heat sink, there'll be some types of material that'll come across that'll be able to absorb more heat and dissipate it in a better fashion. And the way we design data centers will also change by looking at not only taking the heat away from the data center, but taking the heat and using it where you basically want to use it. So say, for instance, people start looking at data centers where they could take the waste heat and actually do good work with it year round, not only maybe low grade heat in the wintertime, but also maybe running absorption machines in the cool in the summertime. So you start looking at some of the technologies from the inside out. So basically, when we look at a design here at Sandia, we look at the inside of the machine and we design out. Now, it's not to say that we're proactive with our big pipes and pumps and stuff like that, because we know what's coming and you're able to place components where they're needed. But the industry trend is heading that way. There'll be some pipe and pipe designs, perhaps, where basically you have a single pipe and you're running a pipe inside with fins with enhanced tubing on the inside and the outside. So you get the heat transfer, but you don't use all the space. So some of these things will be coming down the pipeline and not so near future. And the way we operate, basically, I look 5 or 6 years from now, I think the computer will basically tell the facilities what to do. They'll find the optimum curve where to place a job is going to take a big percentage of the nodes, which is like 80 or 90% of the job. Through machine learning and AI transfer, they'll basically tell the facilities, hey, get ready, we're fixing to place this job at the optimum curve. We're going to use 80% of our energy, but on the optimum curve on our cooling and our power, this is where we're going to place this job. Thank you.
Yeah, Dave, I think when you look at it at a data center level, right, a few years ago, I would have said AI is going to change the world. Right now, AI is changing the world, right, overall. When you look at it at a data center level and you have these massive supercomputers and you know, a lot of more and more of their AI capable supercomputers, right, built for more and more AI jobs. And yet data centers are so dumb, right, today. And they need to be less dumb in the future and use a lot more of that machine learning to actually interface with the computer, or as Dave says, you know, have the data center controlled by the computer. It makes a lot of sense. And I think we have to head there. And that's where a lot of the, I'll call it low hanging fruit is, in terms of really getting more efficient data centers for HPC clusters, right? There's other technologies, of course. Immersion is making a bigger and bigger play every year, right? And it's kind of at the point where there were a few companies, and that's kind of exploded. And there's a lot of different companies looking at it, which certainly has challenges, you know, in terms of there's some maintainability, you know, concerns, signaling concerns, but it's a promising, you know, technology. And, you know, moving ahead, and if we continue to see these higher temperatures, you know, two-phase, there's companies out there right now that are doing some pretty novel work on very efficient two-phase cooling already, and some of them with established data centers. So that's looking really, really promising, right? And then you know, at the chip level, we've got to do, and we're really focusing on, you know, doing a better and better job of lowering the thermal resistance, you know, and making the chips easier to cool even as the power goes up and up. And I think, you know, obviously I can't talk about what we are doing in the future. There are innovative technologies, but I think you're going to see a lot of focus on that, right? It's not just slap a cold plate on it and run it out to a cooling tower and we're good enough. We're going to have to start thinking of it very early on in the design phase of the chips, of the boards, of the servers, et cetera.
Yeah, and Sammy, you know, you talk about immersion. You know, one of the projects I'm working on right now, we're doing a large scale single phase immersion design and deployment, and it's for everything AI, ML, HPC. All those workloads, you know, that it's being designed for. But one of the key design elements of it, because of some of the higher temperatures that immersion able, while still maintaining the overclocking compared to some other technologies, is we are doing heat recovery and reuse. In our particular application, we're offloading the heat to an indoor greenhouse, commercial scale greenhouse that's being grown or being built, I'm sorry, for an area that has a very hard time producing fresh produce. Last week when I was at the OCP conference, I was able to moderate a very interesting technical paper by a company that is actually looking at heat reuse outside of the realm of the time of year. They're actually doing heat reuse in the Persian Gulf, where they're actually using it for desalination. And what they're finding is by using it for desalination in that type of scenario, they can actually get almost full heat reuse and recovery year round, regardless of the outdoor ambient conditions. So I think there's a lot of interesting things coming down the line relating to that. Lots of challenges for how to do it efficiently. But when you start getting into heat reuse, the other thing that becomes interesting is you can very easily start to monetize the infrastructure that you're putting in for that heat reuse, even if you're offloading it off the site, because you can sell those BTUs or those therms to whoever that heat host is. And that actually becomes a revenue generator for the facility.
All right. So we do have a few more minutes in this part for this section. I was wondering if anyone could kind of address maybe some of the innovative technologies or ways that are the HPC facilities are looking at data coming in from the facilities and from the HPC system itself, and trying to merge those things and get things to be shared between the two. Because, in the HPC world, we have all these different groups that are making the HPC system work. And it takes, all those people have their specialties, and it takes a really integrated design and effort to come together and really get things to work as efficiently as possible. So can anyone speak to maybe that, data analytics, and both on the control side, facility side, as well as the HPC side, and how does that look? How's it shaping up for liquid cooling and optimizing that?
The Sandia side, we're just starting to get into that. It's funny you bring that up. A lot of these systems, we're always tail wagging the dog. We're doing feedback, we're doing reactive, we're constantly trying to catch up. It would be really nice to be able to talk to those computers and let us know, hey, what's coming up? How fast is it going to come up? A lot of these systems change their loads much quicker than the mechanical systems can catch up. So integrating these together is going to be key in the future. The problem is the manufacturers they're proprietary. They really don't like to do that. So we're going to have to force that. Otherwise, we'll always be in this catch-up mode.
We are working on tagging applications which are changing their heat load on a very high basis and very fast, because that's the problem for the cooling infrastructure. If the supercomputer changes the power consumption from, let's say, 1 megawatt to 2.5 megawatt within milliseconds, that's a problem for the electrical distribution systems and also a problem for the cooling systems. And that's a special problem of supercomputers or supercomputing.
And I think one of the other challenges that you have when you're doing the reactive type models is that while the compute of the HPC cluster can change very rapidly and the electrical load change very rapidly, HVAC systems do not typically change rapidly. So there's always a delay response from the HVAC system because just because of the dynamics and the physics of the system. That's one of the things in my mind that makes it to where a predictive type model, something where we're feeding forward from cluster to the facility, what's getting ready to happen, would be a fantastic advancement, because then the HVAC system could actually already have gone through its transitional period and be ready to go by the time the cluster spools up.
Yeah, that's exactly right. That's exactly what I was talking about, is with the AI and machine learning. So we're working with some of our HPC team here, and we're using the Splunk as a go-between, as a gateway. We have a decent tool at Enlight. We're gathering metrics now, watching jobs run when they're queued in there in the system. So we want to enable the cooling system hours before a large system would run on the computer. So basically, we would get, if we had cold storage or whatever the case may be, it would proactively get ready for that large job scale running, and also notify the utility users. Basically, we're going to be running this job. When's the best place? That's what I meant by optimum curves. When's the best time to put this job in the curve of the power, so our power purchasing could be at the cheapest as well as the optimum curve.
All right, we do have time for one question before we move on to the next question. So in the chat, this one was from Aaron to Sammy. You mentioned two-phase and thermal resistance. Would be curious about the panel's thoughts on that relationship in T-case temperatures.
Yeah, it's an interesting question. So there's a lot of advantages to two-phase cooling, right? Advantage number one is Herbert, I think it said earlier, is you get to raise your inlet temperature up, right? Which helps everybody. But then when you start looking at how flow boiling actually works and look at a boiling curve, you actually end up with a lot more consistent temperature, no matter, regardless of the power. And you can almost get isothermal within a pretty wide power range in terms of the chip, because of the way that the annular boiling regime works, right? And so the two-phase cooling not only allows you to do a lot of the things data center wise because of the higher inlet temperature, but it also brings down your thermal resistance inside your cold plate, and it also keeps your chip temperature a lot more constant, regardless of the power, or almost regardless of the power that you're actually running at, which, by the way, also has some reliability benefits as well, right? There's a lot of challenges that go along with all of that, but I think hopefully I answered the question on at least some of the benefits.
All right, thank you, Sammy. All right, we'll move on to question 4. Do these higher temperatures challenge the maintenance of water quality? How can we specify and maintain high water quality in the heat transfer loops?
Yeah, well, this is Dale, and you're right. Water quality is a big challenge. We're developing an open water treatment specification with a limited wetted material list, and it's been much more complex than I ever expected. It is important to note that the wetted material list and water treatment go hand in hand. So as we try to, as we're challenged with multi-metal systems, the water treatment issues increase, as does the point that as the temperature increases, that makes it a little bit more difficult as well. There's a lot at risk in terms of doing it wrong, but also it's very expensive, the treatment and the monitoring. So it's important to take a graded approach relative to the size of the system and the criticality of the system as we look into the optimum water treatment plan. But I think we should go to our water treatment experts on the panel and hear from them. Mike?
Hey, thanks, Dale. I'm phoning in from over here in Europe. They were having that big COP26 conference they just wrapped up. So we've been talking, 26 years about saving the planet, reducing our carbon footprint. It sounds like there's a lot of action around that, a lot of government goals around that. I don't see that letting up. So Dale, I think what I'm hearing from Herbert and John and Vali and Dave and Sammy is, warm water computing definitely moves the needle in the right direction around reducing our energy consumption. So with that in mind, and really the overarching pressure that everybody will be under in the years ahead around this whole carbon goal setting process, I see definitely more, warm water coming into play, not only in HPC, but really where it's going to move. And I'm hearing from a lot of the panelists that you're seeing this convergence at hyperscale. And, we're seeing a lot of that ourselves in hyperscale, where the water is starting to, move into the cold plate. So really those two systems, you've got the open system, you've got that closed system in some deployments. As you warm the water, two things happen that are important to understand. One is, as water temperatures increase, corrosion rates increase. And as water temperatures increase, microbiological activity increases. And it's pretty simple to think about, if you leave your milk out on the kitchen counter for a day, it kind of starts smelling funny after, a day. But if you put it in the refrigerator, it, you keep it there a week or two with no activity. So, temperature, it's not linear, it's logarithmic. So that's for corrosion and microbiological. So, is air cooling going to go away? I don't think so. If you look at the price of air-cooled Porsches today, the old ones, there's a lot of activity in air cooling engines and computing activity out there in hyperscale and HPC. But I think we're going to start to see a lot more water. So the other thing that, when you start to close these systems off in these small micro loops in the HPC environment, Dale, I think there are really a couple of things that we try to educate people on in the industry. And, the first is really build it with the right materials. You mentioned, you've got a very limited materials list that you're looking at in your project, but these materials just seem to have a way of creeping into these projects. Nobody kind of knows how they get there. These vendors just put what they want in there. And we spent a lot of time on a lot of these projects really getting into that materials list and, trying to build systems that are capable of being treated. Everybody thinks there's this special magic wand that water treatment chemists have that they just wave over, any kind of water, and it just magically makes it all work. But unfortunately, there's only so much you can do with the chemistry of water, and water's amazingly aggressive. I mean, it's the universal solvent. It makes most of your body. It really drives the planet. And it is, extremely aggressive to most materials of construction. So removing materials of construction is the one thing we really try to get involved in early in the project, right? So let's get the material to something we can treat, and then let's get the right treatment regime in place so that it actually works. That's a step that often gets kind of missed in both HPC open and closed side. So we really need to take a real hard look at that. And then, assuming all that happened, we really like to get involved with the manufacturers of these systems to help them build it clean. And when I say clean, I don't mean like physically clean, like it looks clean. I mean like sterile clean. Because especially on these micro closed loops in the high performance compute and now hyperscale environment, these bacteria, once they're introduced, and I'll use the example of little fittings that go into a process. And you think about one single fitting that maybe was cut in a machine shop with a die that had cutting oil on it, that maybe hadn't been changed in 2 or 3 years. So that cutting oil breeds all kinds of bacteria. That one single fitting that goes into the system, that one single fitting, I mean, that's like COVID attacking America. How long did it take? Like a week? I mean, from China, it didn't even take a week. I mean, it landed in Seattle. Next thing you know, it's in New York City. I mean, that's your high performance compute environment. I mean, that one single fitting that this manufacturer used like dirty cutting oil on, and your manufacturer shipped you in this nice sterile looking baggie that looked perfectly clean, but it just completely trashed your system. And when you look at warm water systems, it doesn't take much. And, we all understand that there's, I think, Herbert, thank you for pointing out the value proposition of warm water. We all understand that's great, but why aren't we doing it? I mean, we've known this forever. This isn't like some new revelation. We should be doing this. It hasn't happened because it's a pain, right? And people aren't taking the steps necessary to build it right with the right materials. They're not taking the steps necessary to build it clean. When I say clean, sterile, and then you got to ship it clean. We're talking about nitrogen layup on these parts, from the factory to the point of application. And we're talking about filling these systems with sterile materials. You don't give a guy a recipe and say, get DI water. He'll go down to the local Kroger store and buy some water. He won't have any, and he'll fill it up with tap water, and you'll trash this multi-million-dollar system right out of the gates. So you really need to get in the weeds on, what exact water are we going to be supplying, and where's it coming from, and what is the quality? And that's, it's a very simple process to follow, but I just see again and again and again, we get called into these projects too late, where they didn't build it with the right materials, they didn't build it clean, they didn't ship it clean, and it's trash. And now everybody wants to go back to air cooling, or they want to, go somewhere else to a different type of cooling because it's a total failure, and they tend to overlook all the great benefits of, what we're trying to achieve in sustainability and really, making a difference with the plant. And then lastly, and I'll close with this, maintaining a system sterile is very difficult. I mean, once you have COVID in your community, it's hard to get rid of, for 14 days. So don't let it get there in the first place. So that's what we really try to preach. It's, build it clean, ship it clean, and then keep it clean. And, so you got to do some monitoring. And if you do all that, I mean, you can fill it and forget it. I mean, if you do all that right, and then you get all the benefits and all the sustainability benefits of that. So it is possible to use water cooling and have zero problems, but you really got to do some pre-planning and lay the foundation. I think as many of you on the call have learned, you've learned some of those pitfalls. So I'm happy to share more. Thank you.
Yeah, I think this is one of the areas that are overlooked most often, right? Because we've all kind of watched the liquid cooling grow in HPC and new vendors coming up and new OEMs getting into the game and everything else, right? And oftentimes you see, vendor A makes a mistake, and it has a lot to do with wetted materials and water quality. Vendor B ends up making that exact same mistake, and the OEMs make the same mistakes, and so do the end customers. And so many of the problems that we've had with liquid cooling in the data center or at manufacturers, revolves around the water quality, right? And this is an area where I think we really, really need standardization. I know we're going to talk about standardization, but if there's an area where we really, really need it, right, this is one. I know I've gotten my own scars, and somebody on this call could actually point a few of them out from bad water quality, right, early on. It just happens, and we really, really need some standardization in this area.
And I think one of the other things that we need to think about when we talk about liquid cooling for, particularly for direct to chip or immersion, because of the temperatures that we're talking about operating these things at, when you're in the air cooled world and you're talking about your chilled water system, for example, you might be talking about temperatures in the, 12 to 20, maybe even 25 C range. That's a cooling system. We get up into the 35, 40 and higher C range. And yeah, it's still technically a cooling system because we're pulling heat out and we're getting it out of the building rather than putting heat into something. But from a water perspective, it's really a hot water system. And so the dynamics are different, the requirements are different, how everything behaves is different. And I think the other part of this, Michael was very eloquent in how he spoke about the challenges with water, but a lot of those challenges also apply if you're dealing with a non-aqueous fluid. When you talk about the immersion folks, their working fluid is a non-aqueous fluid. They have their own set of requirements. A lot of them are incompatible with EPDM seals and whatnot that you find in traditional hydronic system gaskets and valves and whatnot. As they run at elevated temperatures, they actually become more reactive with the other materials around them, much like water does, and so they can become contaminated more easily.
David, I'd like to hear from David Masuda, see how he'd like to add to this conversation.
Sure, thanks. I'll jump in. I think I could probably spend a whole day talking about this, but I've got 2 key points that I'll bring up, and I'm with Chemtreat, and I'm kind of on the front lines is my role. So I typically deal with these types of systems directly as a water treatment vendor. So when it comes to maintaining high water quality, regardless of the temperatures, but specifically more important when you're going to higher temperatures, I'll bring in, I have 2 points that I just kind of wanted to communicate. Where I see applications fall flat on their face, first is in integration. And that kind of goes back to the point that Mr. Lesniak made around, shipping it clean, making it clean, and integrating it into a clean system. At a larger scale, what I see out on the front lines is, right, we'll bring in this new technology. We're highly focused on protecting the investment of the new technology. But I think that what can often happen is the integration into the larger, I guess if you want to call it eco cooling system that the new application is tied into, it can be overlooked. And again, great illustration would be, you bring in, a new computer system, you tie it in with all of the, into an existing system, and we've done all the metallurgical analysis to make sure we're compatible locally, but then we overlook, some type of metals or, other components in the system that are either upstream or downstream that end up causing us problems and headaches down the road. Or we end up integrating into a system that wasn't, biostatic or sterile to begin with. And then we, with the new technology operating at higher temperatures, that part of the system sees a much greater impact than the greater system, which is, operating at conceivably temperatures that are 20, 30, 40, 50, 60 degrees cooler. So I think integration is a really important piece of the equation that needs to be further evaluated when it comes to maintaining higher water quality. And then the second point that I'll make is around the ongoing, maintaining high water quality. And the point I want to make there is that what I see, and it's kind of force of habit or, how things are done. But water treatment, when it comes to maintaining these systems, can be a very reactive approach, especially when it comes to like biological control, right? We're looking for bacteria, and if we see it, we address it. So, from a larger standpoint, if the goal is to maintain high water quality, regardless of the temperature, then, anything that can be done from a proactive standpoint to make sure that corrosion and biological growth are mitigated ongoing, basically squash that bug before it has a chance to grow, is really going to be in the best interest of the application. So that's
All
my
right.
2 cents.
Thank you, David. We do need to move on to the next question. This is the last question, and then hopefully we'll have some time to address a few of the questions that we haven't gotten to yet. So with every computer refresh, retooling of the facility is required. This adds to the complexity of installation and potentially takes away from time when the computer is doing mission critical science. Plus it adds to the operational cost. Can liquid cooling infrastructure be designed to facilitate refreshes of new equipment? Is there an opportunity for standardization?
Well, of course, there's a good opportunity for standardization and open specifications being developed by the OCP project as well as ASHRAE can help. Probably more on the commercial system front, like our clusters, rather than standalone supercomputers. But we have a lot of HPC in the clusters, and standardization of how those are cooled is a big opportunity. I think other areas of standardization that's important to future proofing are the W specifications for water temperature. That was the first standard, I think, that was developed for liquid cooling, and a very important step. Another future proofing challenge relates to the potential for multi-temperature systems. I think John described that a little bit earlier. But besides being a challenge, this is also an opportunity where the effluent from the coolest running system can be the supply to the next. But this does require good access and to your plumbing system and flexibility in your plumbing system. And so that needs to be thought out in the design in terms of future proofing the facility. John, did you want to add something?
Yeah, I do. So, you referenced the Open Compute Project, OCP, and we are working on that actively right now. There's actually 4 groups involved with that. There's one that's focused on rear door heat exchanger solutions. There's one that's focused on cold plate. There's one that's focused on immersion. And then the one that I'm actively involved with is the one that's focused on how those different solutions interface with the facility. We've already published a specification last week, actually, that talks about the means of connection between the compute and the facility based on the pipe size. We're working on trying to standardize performance envelopes for the facility side, working pressures, temperatures, pressure differentials, because that affects obviously your pumping. We're working on all those things right now, and it's still fairly early on in the process. We just started the effort about 18 months ago, and we're continuing to kind of move on through it. But there's a lot to it, as you can imagine, because we can hook up the connections for one manufacturer's solution to the piping the same way we can another's. One of the other challenges that we have is form factor, and I've been kind of telling people I view the current scenario to be similar to how air cooling was 15 to 20 years ago, where a lot of manufacturers kind of had their own form factor for their racks, and you couldn't necessarily bay them all together. You couldn't really put them next to each other with good containment and so on. I think that's kind of where we are with a lot of the liquid cooling, and with time we'll start to see some convergence to make it even more modular.
Hey, Dale, it's Michael Lesniak here. So my wife takes her, $100,000 car down to the oil change place, and she decides to put, 10W30 in her new high performance car that runs on synthetic only, right? With 12,000 mile intervals. And, she lets the guy in the, quick lube place decide on what to put in there. Right? Would you do that? I mean, of course, I had to chew her out when she got home. And what in the world are you doing, honey? You should pull out the owner's manual that tells you exactly what to put in this thing. And at least she has an owner's manual. She still doesn't follow. At least it says exactly what to do. She didn't do it, but we got over it. So the thing we struggle with is there's like no owner's manual that tells you exactly what to do. You invite in these, we call aqua bobs, to tell you what to do with your, multi-million-dollar system. And like, who gives them the authority? I mean, who gives the quick oil change guy authority to put oil in my wife's $100,000 system? You know what I mean? Like, what does he know about that? I mean, does he really know what's under the hood of that thing? I mean, this is what's going on. It's ridiculous. I don't understand it. So we need to have standards. There's science involved here. And we need to apply science, and it's sorely missing. So, Dale, the work you're doing has been awesome. I'll leave it at that.
Can I, if I can jump in, I think, Michael, you brought up a really good analogy, because we do live in a world that has a few different grades of oil. It does have synthetics, and assuming we're not ignorant and just put whatever seems to fit the bill, or if I can pour it into the order of work, that obviously doesn't follow. But the idea is that we live in a world where multiple options are available. And I think when it comes to liquid cooling in particular, we would love to be able to standardize on a facility cooling water temperature following that same methodology. Let's just say 40C happens to be a good value, because you can get 40C water almost anywhere on the planet passively without chiller plant, that means. And in some cases, it may not be the right temperature. So for HPC applications or for other type of needs, we may need cooler water to be able to give a little bit of a kick or jump start to the facility that needs maybe 25C water. Unfortunately, if you have a facility that has both 25 and 40, you would either produce the 25 water and mix it or blend it with a return to, or other possible notions to get to the 40. That's not efficient. That's actually a really bad way to do it. And you can't produce 25 water from 40-degree water. So you're really kind of stuck in that situation where you have to live in those two separate, very diverse environments. So with the W ratings, the fact that we have different 4 or 5 different categories of temperature, if we can get people to at least converge on those values as a starting point, then for certain applications use 40, for certain applications, especially with heat reclaim, you might use 45. For the high performance compute, you probably, to get the extra performance out of the processors, you will definitely need cooler water. You may need a chiller plant. The good news is you don't have to size your chiller plant for the full capacity of your data center. You only do it for the loads that you expect to be that HPC load that needs the lower temperature water. It's not ideal, but there are definitely synthetic oils and there are definitely the regular oils, and we most of the time do not make the mistakes of mixing those up. Just my take. Thanks for that analogy, Michael.
Well, on this topic, I think Herbert said something that was very interesting earlier on in the talk, and that was, if you require it, they will build it, right? And I think it was Supercomputing 2015 or something, we got asked the same question. And my response at that time was sort of, if we could get the customers to pull, it would be as effective or more effective than a standards-based body putting out a standard. In other words, if everybody in the public sector in Europe and all the major ones in Europe and the US got together and said, you know what, we're going to give a set of pipes every 5th tile with 6-inch flanges, whatever, and that's what we're going to write into our RFPs, right? Whatever they all decide on, and start standardizing amongst themselves, then that's what the OEMs are going to build to, right? And that's a really good way. But if you look at the RFIs that are out there, they're really not standardized around the data center. So it seems like there can be some work there on standardization that's more of a customer pull than anything else.
Yeah, and I think some of that, Sammy, you talk about the market pulling forward and kind of where we are now, is I think you look at the OCP pathway that's being used to try to get there, and OCP, as you may know, is really just, it's an organization of users and providers that are trying to do that, to get the industry kind of pulling in the same direction and turn to the ITE solution manufacturers and say, this is what we want. And when we start aggregating enough of us together, there's a significant portion of the market here that's asking for this. And so the manufacturers will respond to it. When I look at the RFP that I helped put together for an HPC expansion just a couple of weeks ago, we were looking at the different vendors that we were evaluating for possible inclusion in that RFP. And they were so vastly different in terms of cooling technology, what percentage was actually being taken off with cold plates versus others, voltage differences. You know, some were 480, some were 415. Right now, I think, you know, if you try to go right you try to go write a tight RFP in terms of the requirements for plugging into the facility, you're pretty much going to end up probably sole sourcing somebody because they are so divergent right now. And, you know, I think where the more voices stand up and say, no, we want to be able to move from generation to generation without completely overhauling our infrastructure. There's ways to do that and not sacrifice, you know, the next generation technology.
All right, thank you. So we do have just a few minutes left. I was going to try to address a few of maybe one of the questions that's in the Hub Slido chat. And I'll do, does liquid cooling have a total cost of ownership advantage over air cooling? Who would like to speak a few words on that? Just a few minutes.
So I would say from the projects I've been involved in, it depends. It depends on your density and it depends on the liquid cooled technology you're looking at. If you're at 10 kW a rack for air cooled, you're not going to get there. You start going up north of 20 kW a rack and you start to look at different solutions where that TCO starts to pay off. The interesting dynamic that I've seen in a lot of these exercises and a lot of these evaluations is the mechanical piece isn't actually necessarily where you're going to see the biggest savings in terms of your CapEx. A lot of folks focus on the mechanical side of it because that's the most clear difference. But when you start going to densities where it starts to make sense, it's actually starting to see savings in your electrical infrastructure. You're reducing the number of nodes that you have because you're densifying. So you have fewer power whips going to fewer racks. You have fewer network terminations. Now they may be 10 gig fiber instead of 1 gig, but you're significantly reducing the counts. And so when you look at it from a holistic perspective, look at the power, look at the telecom distribution, look at all the infrastructure associated with that, that TCO advantage starts to come in a lot sooner than you might expect. And with some of the stuff that I'm working on right now, where we're in the 50, 60, 70 kW per rack range, it's actually a lower CapEx because of those electrical and telecom scenarios that I was just referencing. And then you have the benefit of the energy efficiency and the water savings. So you're actually cash flow positive the day that you turn on the servers.
If I may, let me also add another element here. We haven't really,
Vali, please.
Pardon?
Go ahead.
We haven't really addressed the differences in the different kind of liquid cooling. And so when I think of liquid cooling, I think of immersion, single phase, immersion, two phase, but there's also the cold plate liquid cooling, which right now seems to be having a faster growth because it's probably a very good transitional technology to get people to think in terms of liquid cooling. So the total cost of ownership when you're doing cold plate is a little complicated because it forces you to do certain modifications to the server itself, in that you have to put the cold plates on. You need the wiring or the tubing, I should say, and you need leak detection. It gets really complicated, but the part that kills the TCO for cold plate liquid cooling is that you also need an air-cooled infrastructure to address the loads that are not liquid-cooled. So typical loads taken away by the liquid for cold plate are about between 60 and 70, maybe 80 on a really optimistic day, but that 20 to 40% of the load of a very high powered cabinet is still a sizable air-cooled system. So if you're going to be buying a liquid cooling infrastructure and an air cooling infrastructure, it's going to get really super expensive, and the TCO does not look so good then for the combined system. Additionally, if you're transitioning from an air-cooled to a liquid-cooled environment, that transition means that you're going to have an air-cooled component for a while, and you're going to introduce the liquid-cooled component. They have to live in the same environment. Again, that TCO doesn't look good. I think that model looks very, very different if you start from the ground up with a liquid-cooled environment.
They do make hybrid RDA or hybrid cold plate systems where you combine the cold plate with an RDHX to take care of that remaining 20 to 40% for that very reason. But not everybody does it.
All right. All right. Thank you, everyone. We are out of time. I'd like to thank all the panelists for taking the time to share their experiences and thoughts. Everyone in the audience, thank you for attending. We hope you enjoyed the conversation. If you are interested in learning more about the EEHPC working group and its many teams, please go to the website, which Natalie posted at the top of the Zoom chat. With that, we'll draw this BoF to a close. Thank you very much, everyone.
Thank you.
Thank you all.
Thanks, David.
Thank you.
Thank you.